Energy-efficient programming is crucial while we consider the influence of the programming execution, computation, and data processing on the amount of energy which is consumed during the process. The research proves that during computation, the processor typically consumes the majority of the energy. On average, the CPU consumes almost 90% of the energy, with the remaining energy consumed mainly by the memory. This is true regardless of the programming language type. It doesn't matter if the language is compiled or interpreted. Energy efficiency became a popular topic in research among my major players in the information technology industry. This goal can be achieved through improvements in hardware technology. Modern processors and system-on-chips integrated circuits implement a selection of power modes, allowing them to turn off the power for unused internal modules. The operating system can adjust the clock frequency to meet the current software demand. These techniques drastically reduce the overall device power consumption, but there is still a potential for further improvements through efficient software implementation. The energy consumed by the computer running the software depends on the execution time, clock frequency, and average power consumption of the hardware. It can be expressed with a simple formula, but in general, all coefficients are directly proportional. In the power, time or frequency increases, the energy consumption also grows. It indicates where one can look for reductions in the energy needs to perform a task. It is worth noting that for the same code, the time and frequency are independent. If the system runs faster, the time of task execution will be shorter. This means that the code efficiency relies on the number of cycles of the software requires to complement the task. This leads to the conclusion that reducing the number of instructions can further reduce energy consumption and make the computation more environmentally friendly. There are two main possible approaches for reducing the number of instructions: improve the algorithm or optimize the executable code. Code optimization is implemented very well in modern compilers. The machine code is generated using techniques that reduce the number of unwanted instructions like loop unrolling. Compilers enable data parallelism with the extensive use of vector calculations. However, because they must be universal, the output code is always generic in some elements, and a good assembler programmer can identify places for further improvement. The most important thing to consider when writing a program in any programming language is to cooperate with the processor and not against it. This includes the proper placement of data in the memory, taking into account both alignment and cacheability, avoiding conditional jumps, manually unrolling loops, and utilizing the maximum possible register sizes available in the machine. There are just a few examples. As a rule, assembly language programming, because the user knows what they want to achieve, usually allows for better code optimization than compiler-generated code. Of course, this comes at the cost of more time spent writing the program and the increased potential for errors. It also requires extensive knowledge and experience from the programmer. However, it is essential to remember that a program written in assembly language does exactly what the programmer intended, and it's not dependent on the fragments of code, sometimes completely unknown when using external libraries.